Today we're talking about the last property of graphing that we're, I think, really going to talk about at all in like high school mathematics. Now we're going to use it throughout a lot of the rest of the course, but this is the last property of a function that we are going to talk about and that we are going to be able to calculate, determine. So we know how to do all these other things like intercepts and asymptotes and critical points. And we're going to learn to find one more new one today, okay? Before we do that, we're going to talk about concavity, as you can obviously see here, but really what we're doing today is just more sketching, but then we include this extra property. If you've taken physics, you already know what concavity is. Like, you know concave versus convex, right? We don't talk about convex. We don't need to. You'll see why in a moment. We just talk about concave, and we look at the curves like this. If it is like that, we call that concave up. It opens upwards, right? We're familiar with that. So this is concave up. And if it opens like this, it's concave down. If you think about it, it makes sense not to call it concave and convex because these are both concave or convex depending on which side you look at. It's not like a physical piece of material, right? That would have one or the other. This one has both depending on if you're looking at it from the top and the bottom. So we call them concave up and concave down. Okay? So you're going to have to sketch this quickly. I think you can sketch it with enough detail. Make it similar as possible to mine, but it doesn't have to be nice because we don't have time for that. I'm going to call those points A, B, C, D. Nice. Looks good, looks good. So, yeah. Are C and D what? No, it doesn't matter. Yeah, it's a good question, but those specifics don't matter. So, this is one way that I kind of think about, I think it helps to think about concavity. If I'm concave up, I could think of it like this, okay? I'm coming down like this, and if I followed that curve, if it's like a car going around a bend and it continued to turn like that, where would it eventually end up? It would end up going up, right? You see how that works? Concave up comes around and eventually will go back up. Now, it might not because the graph might change. Oh, we forgot to write one thing down. I'm going to go back and write that down. A point of inflection is where the graph changes concavity. Okay? A point of inflection is where the graph changes concavity. So these are the points that we're going to be able to calculate and put on our graph. Remember, just like we learned how to find critical points, local max, local min, just like you used to put the vertex back in grade 10 on a parabola and locate that point or whatever graph you were looking at, these are going to be new points that we can graph. When you do trig functions, you have to locate 5 key values. Not in calculus, though. In trig calculus, it's different. Okay. So if I'm coming around a bend and I'm concave up, eventually I'll go up. If I'm concave down, I'm coming around like this. If I'm coming around, eventually I would go down. But again, maybe not, because there might be a point of inflection that changes that. So what I'm saying is not necessarily the graph eventually goes down, but if you followed that curve, eventually you go down. If you're coming up and around and you kept going around, you would eventually be going down. Does that make sense? See what I mean by that? But you understand that it doesn't mean the graph actually does. So what do you think is, and I think it's fairly easy usually, especially once you get used to it. There's not much of a trick in most cases. There's a couple of little tricky spots. But so is point A in an interval on a location on that graph that's concave up or concave down? It's down. Good. Is that what most people were thinking? Yeah. And B? Concave up. Very nice. Thanks. So what does that mean? This is the part that's tricky, but thankfully this isn't something we usually need to do. Picking out a local max or min is fairly easy. You can kind of see, like if you have a curve, you can kind of see where the horizontal tangent line would be and locate it pretty accurately, don't you think? If you were looking at a graph. Points of inflection are not like that. Points of inflection are like, well, it's somewhere around here. So somewhere, like to me, this looks clearly concave up. This looks clearly concave down. So somewhere in there, there's a POI. But where exactly, I don't know. Like I can narrow it down, but it's to me, it's hard to tell. And sometimes it's way harder to tell than others. Sometimes it's easy to tell. But often it's tricky to pinpoint. But that's not something we have to do because we can calculate them by the end of today, hopefully. So we don't need to eyeball it. We'll know where it is. Okay, what about point C, concave up or concave down? Say again? Down. And D? Down. Still down. That's right. It has not taken a turn. It's still curving down like that. It hasn't started curving up or anything like that. Okay, so no point of inflection there. Very good. Okay, one more. Oh, I've missed something. We'll go back and do it after. Oops. This is what happens when you rush. You forget things. It's kind of important too, what I just forgot. But that's okay. We'll go back and do it. It's kind of like the whole point of today. Forgot. And so you know, there is a horizontal asymptote here. Okay. That is approaching. Okay, so we've got points A, B, and C. Is everybody kind of with me now? Got that drawn more or less? So point A, what do you think? Is it concave up or concave down? Down. Point B, concave up or concave down? Good question. And that's what I mean. It's really hard to tell, isn't it? It's not. So it's probably still down, I think. Yep. So we would, I mean, this is not, we don't put questions like this on tests, and it's not like we put one really close and like, ha, got ya. It's actually not, like, that's not something that we do, right? So don't worry about it. And then concave C, Bradley, what do you think? Yeah, so you knew that it was switching from one to the other. This is the case where it's really, really hard to tell where exactly that point of inflection is. It is probably somewhere really close to B in there. Maybe, I don't know, maybe it's a little bit further. I don't know. Maybe it's a little bit further here. Whoops. Somewhere like that. But there's definitely a POI in there somewhere. And this is something that's tricky that some people do get confused because they confuse increasing and decreasing with concavity. So if this is approaching an asymptote, it's always decreasing, but it's also always concave up. Because if it was concave down, it would go like this and it would cross the asymptote. So even though it's decreasing faster than it's turning up, but it never turns down. So that's what makes it an asymptote. It's this interesting balance between how fast it's decreasing and how fast it's curving makes it an asymptote. Okay, but it will always be concave up. And in fact, that's a fact that you could memorize if you wanted to. If you're approaching a horizontal asymptote from below, you're always concave down. If you're approaching a horizontal asymptote from above, you're always concave up. Like that will happen, but people make a mistake because they think it's always decreasing, so they call it concave down, but it's not, it's concave up. So I'm going to go and add that up here. That's not what we forgot before. Just very quickly. Whoop, I did this backwards, didn't I? No, I did this right. So this will be if I'm approaching a horizontal asymptote from above, I'm going to be concave up. And if I'm approaching a horizontal asymptote from below, I will be concave down for the entirety. At some point, there's a point of inflection, and then it'll always be concave down from there on. Does that make sense? But that it can be a tricky one. That fools people because they think it should start going up at some point. So when I said before, you can think of it as if you follow the curve around, it'll eventually come up. That doesn't actually happen. You can just think of it that way when you're thinking about whether it's concave up or concave down, right? You can also think of it's a parabola opening up or a parabola opening down. Like there's different ways to think about it. The important thing that I missed is this little blurb right here. What does the second derivative tell us about the original curve? Well, obviously it tells us something about concavity. What does the first derivative tell us about the original function? It can, the turning points, and what else? Whether it's increasing or decreasing, which is related to whether there's turning points if it changes to increasing, decreasing, right? Very good. What about the first derivative tells us if it's increasing or decreasing? Thank you very much. Whether it's positive or negative, it's interesting how these are things you can do, but then when you're asked the question, it can be hard to come up with that answer. It's interesting, isn't it? Maybe, hopefully more of you were thinking that, but if the first derivative is negative, the function is decreasing. If the first derivative is positive, the function is increasing. So the second derivative tells us about concavity. So if concavity is down, what do you think would be true of the second derivative? Just a wild guess, whether you're right or wrong, doesn't matter. Yeah. If the second derivative is negative, the original function is concave down. If the second derivative is positive, then it's concave up. Easy enough, right? Positive, up, negative, down. That's easy, hopefully. Okay, so down, down, up. But again, normally what we're doing is we're testing the second derivative to determine the concavity, then drawing the graph. In this case, we work backwards. We were given the graph, we were able to look for the concavity, and then figure out if the first derivative would be positive or negative. Any questions about that? So everything we've been able to do up to this point, which is intercepts, asymptotes, and critical points, and all the behavior obviously that goes along with those things. And now we're adding on points of inflection. And then that's it. There's nothing else. So I'm going to do this one a bit differently. Yesterday we talked about how we can expand, and that can help us. Let's try not expanding and see what happens. We can factor, though. I think we might want to factor this. So this will be 3 plus x, 3 minus x on top. And we're going to take all the derivatives. So there's a lot. This adds a lot of extra work. It's a simple idea that if the second derivative is positive, it's concave up. Second derivative is negative, it's concave down. Simple idea, but that means we have to take the second derivative. And to take the second derivative, we need the first derivative. And we need the first derivative for critical points anyway. So we have to do the first derivative and the whole second derivative. Thankfully, we don't need a first derivative chart. We can get away with just a second derivative chart. So if you're doing both charts, you're wasting your time. I've seen people do that, but it's a waste of time. They're people not paying attention. Okay, second derivative chart only. But it is more work. And if you make a mistake taking the first derivative, your second derivative is going to be wrong and like, oh my gosh, it was supposed to factor, now it doesn't factor, and it just everything falls apart. So, our first derivative, what do I have to think about when I'm doing the first derivative? Quotient rule, which is derivative of the top over derivative of the bottom. Isn't that right? Am I remembering correctly? No? Okay. So, got to use a quotient rule when you're doing these. Again, if you're practicing, you're always going to, but if somebody wasn't paying attention, that could be a problem. So the derivative of the top is, whenever it's minus x, it's a little bit trickier, right? Sometimes we miss the negative sign, but it's negative 2x times the bottom minus the derivative of the bottom, which is power of a function rule, so 2x plus 2, but the derivative of what's inside is just 1, so that's it, times the top. Over the bottom squared. X plus 2 squared all squared is x plus 2 to the 4. I'm going to factor out the negative and the 2. And all I have else is an x plus 2, because I've got x plus 2 in both. This one's left with x times x plus 2. I factored out the 2. I factored out the x plus 2, so I'm just left with 9 minus x squared. That's gone with that. Cleaning things up. I factored out this negative. That should be positive. Sorry, did everybody catch that? I factored out that negative. That should be plus. I knew something was wrong with that. So this is plus 9 minus x squared last step. X squared minus x squared is gone. I get 2x plus 9 over x plus 2 all cubed. You're all frantically writing to keep up, but I hope you're following that. Cleaned up pretty nicely. Don't you agree? All done? No, we're not all done. We got to take the second derivative. Yikes. So imagine if this was quadratic still, right? Like you made a mistake and this was quadratic. It's got an easy place where it's equal to 0 and you turn it into something that's needs a quadratic formula or isn't solvable. So like all kinds of things can happen. Are we okay? Ready to continue on? Oh, I didn't mention this. We talked about this briefly before, like a while ago, I think. But for second derivative, it's just 2 tick marks, whether it's function notation or with a y, right? And then third derivative. And then fourth derivative, actually, instead of just continuing with tick marks, I think the standard would be like Roman numerals. You'd go to an I and then a V. But we don't, I don't know that I've ever taken a fourth derivative of something. So we just do first and second, really. Okay. So again, oh, somebody asked a great question this morning. To take the second derivative, would you put this -2 back in there? Sure, you could. Or you could just factor it as is, like it's irrelevant for the factor. Or you could just take the derivative as is because it's sort of irrelevant for the derivative, right? But the other thing, if you think back to limit properties and properties of derivatives that we talked about a long time ago, is I can actually, I can take it all the way out front and then just take the derivative of what's left and then hold on to it for at the end. So up to you. Those are 3 different ways that you could do it. They're subtle differences. You got to find which one works for you. The derivative of the top is just 2. I'll show you why that works in a moment as well. I think you'll believe me. Times the bottom minus the derivative of the bottom, which is 3x plus 2 all squared times the derivative of what's inside, which is still just 1. Times the top. Now I've taken out the -2, so the top is just 2x plus 9 over the bottom squared, x plus 2 cubed, all squared is x plus 2 to the 6th. So think about this. If I had left the -2 in, this would just be a -4, or it'd be -2 times 2, because the derivative would have been -4. It would have been -4x, right? And I would have had the -2 in here as part of the top. And then I just factor it back out. Think about it. If I had that -2, if I use it in the derivative, it would just be in here, and I'd factor it back out anyway. So if you have a constant that's multiplied out front like this, it's the constant multiple rule, if you remember from last unit. I can just pull it out front when I take the derivative. Okay, now we got to clean this all up. So I've got -2 out front. And then I've got just an x plus 2 squared. So I've got a 2 and a 3 and a 2x plus 9. None of that's in common, but this has x plus 2 squared and this has x plus 2 cubed. So I can take out an x plus 2 squared. And I'm left with 2 times x plus 2, because I had 3 of them. I took out 2, so I've got 1 left, minus 3 times 2x plus 9. The x plus 2's are gone with the 6, and I'm left with 4 of them, which makes sense. That denominator always increases by 1 every time you take the derivative. So that's a pattern you should look for, and it should sort of work out as you're factoring and simplifying. Okay. So now I have -2 2x plus 4 minus 6x minus 27. I'm going to do this in 2 steps. You can only, if you only want to write down one, that's fine. This is negative 4x minus 23. Am I going too fast? Does it feel like to you like I'm rushing? It's because I am, because there's so much to do. Cleaned up kind of nicely. They don't always, unfortunately. Those are on the easier side of derivatives and second derivatives for this stuff. Any questions so far? I mean, that's all stuff we already know. This is why we worked so hard in the last unit. And some of the stuff we did in the last unit was way harder than this. That's why we worked so hard on that, is because we need to be able to do this without making mistakes. Just for your own sanity. Because when you make a mistake, man, things start to fall apart. Any questions? So this is my second derivative. And this is my first derivative. Now we got all that done, we can move on to, what are we looking for? Intercepts. So take a look with me. If I put 0 in for x, this is what I was saying before, like we didn't expand. So finding the intercepts and the horizontal asymptote feel a little different. But if I put 0 in for x, that goes away. So I got 9 on top. 0 in for x, I get 2 squared on bottom. So my y-intercept is just 9 over 4. Not that hard to do, right? Follow that okay? X-intercepts are plus or minus 3 from the factored form. So again, 9 over, if I expanded this, it would be x squared plus 4x plus 4. So 9 over 4. Asymptotes. Start with vertical asymptotes. What do we have? Yeah, x equals negative 2. We only have the 1. Okay. You might want to watch. Put your pencil down and watch. If I could use this form if I want, but I'm going to use this form. And again, this is where efficiency and proficiency save you some time if you know which is the easier of the two forms. Now, that's different for different people. It might not be easier for you, but if I'm approaching negative 2 from the left, so negative 2.1, I'm going to square it. It's going to be about 4. What is it exactly? I don't care. It's about 4. Positive 4, because negative 2.1 all squared is positive 4. 9 minus 4 is positive, right? Still positive. So sure, negative 2.1, I can't square that in my head, but I know it's about 4. It's not going to be more than 9. So it's going to be less than 9, so this part's positive. When I put it in here, I get a negative, but when I square it, I get a positive again. So I get positive over positive. So this is positive infinity. And when I approach negative 2 from the left, negative 1.9, this is still about 4, so positive on top. This is all positive on bottom, so positive on positive, so still positive infinity. Horizontal asymptote, what is it? Yeah. Why is it negative 1?
On the top, you have 9 minus x squared, so I just knew that that was negative 1, and then it was over, if you expand that, it just gives you x squared.
Yeah. Exactly. So again, expanding this in your head, you get x squared on the bottom. You got negative x squared on top. Negative 1 over 1 is negative 1. So if that's something that's easy for you to do, you may not have to expand depending on the situation. There might be other situations where it's better to expand. If everything works out to ones, it's probably not so bad. So if I let y equal f at x, I can use function notation. I'm going to do that now because I just like to write it this way. And I've already got these done, so I'll write them down for us. But you're punching this into your calculator, into the original function to determine that this is negative 1.04 and this is negative 0.96. Oh, so they're both negative. Of course they're both negative. The asymptote's negative. That's not what we care about. The three, well, you talked about this yesterday, the three kinds of asymptotes, mix and match, they're how you do the testing. For vertical asymptotes, I care if it's positive or negative. For oblique asymptotes, I only care if it's positive or negative. Right? But for oblique asymptotes, I'm punching in an actual value, probably, maybe not actually, you don't always have to. But for horizontal asymptotes, you do, and you need the actual value, and then we decide if it's above or below our asymptote. And again, it matches the asymptote. So if I had this as negative 3 for some reason, and then these are the values that I'm getting, I'm like, okay, something's wrong here. Okay, but this is below, and this is above. Done with asymptotes. What's next? Critical values occur when the first derivative equals 0 or does not exist. You don't have to rewrite this. I am just so I have it on my screen and I can talk about it. I always start with where it does not exist because I'm scared that if I don't, I'll forget to do that. Where does this not exist, if anywhere? At negative 2. What do we know about that location? Very nice, the vertical asymptote. So once we determine that, if we were doing a first derivative chart, we do have to include that value. We're not doing a first derivative chart. So we already know that that's a vertical asymptote. Whether it's increasing or decreasing can change. In this case, we don't need to worry about it, but we still need to do it and check because it could be relevant. Where does it equal 0? When the top is 0, so it looks at negative 9 over 2, which is negative 4.5. Done. Not doing a first derivative chart, so we're done. Point of inflections can occur when the second derivative is 0 or does not exist. They don't necessarily. This is a minor detail that you wouldn't care about at all, but sometimes teachers care about it or mathematicians care about the specifics of the language. We call these critical values, not critical points. Because it might not be a point, it might be an asymptote. So some people would say, don't call these points of inflection, call them possible points of inflection, which is fine. That's what I will call them, but POIs can occur. We're not saying there are points yet. We're just saying they might be here. They do occur at these locations, but we're going to check later and see if that's what it is. Usually it is, not always, but they can occur at these points. Does that make sense? Minor detail, you probably don't even care. Okay, so first of all, the second derivative does not exist where? Oh, I'm going to write down the second derivative again. Where does the second derivative not exist? Negative 2 again, right? I hope you noticed that. Still where the denominator is equal to 0. But again, that's a vertical asymptote. So see what happens? Like, we already knew it was a vertical asymptote. We already did all that testing. It keeps coming up in the derivatives, and that's pretty much always what happens with these rational functions. We still do it, but then we call it a vertical asymptote, and we don't worry about it. But it does belong in our second derivative chart now. Absolutely belongs there. Okay? Where does this equal 0? When the top is 0, which is negative 23 over 4. Everybody good? Now our second derivative chart. I'm only looking at my points of inflection, my possible points of inflection. The hardest piece of mathematics you're going to do all day today. Which one comes first, negative 2 or negative 23 over 4? Because I never learned how to do fractions, so I don't really know which one's bigger. Does anybody know which one's bigger and which one's smaller? What do you think? Negative 2 is bigger. And we start with the smaller one, so we're going to start with negative 23 over 4. It's negative 5.75. Turn it into a decimal if you have to. We often do that. Negative 5.75, so it is definitely smaller. So x less than negative 23 over 4. Never write that as equal to. I think I've seen a couple of people doing that, but we haven't had a chance to point it out. That is not equal to. That's wrong because it's equal to in the next line, right? Because something happens at that point. So don't include that point ever, ever. For every one of these charts, it's just less than, just greater than. Never equal to. Negative 23 over 4 less than x less than negative 2. Negative 2, x less than negative 2. Now, at that location, it's 0. At this location, it does not exist. Yes? Thank you, yes. Now, we're going to do some testing. I'm going to show you how you can plug this into your calculator in case you haven't seen it before, but I'm going to do it very fast because we don't have a ton of time, although we're a little bit ahead of schedule because we rushed. So if there are questions, stop me and I can answer questions. Okay. So I'm going to switch over to this. And I got my calculator here. And I am punching. I'm going to cover up the graph because I don't want you to see the graph. I'm going to cover that up because I don't want you to see that. I'm punching this second derivative into my calculator so that I can quickly do. We only have to check 3 values, but you could easily have to check 5 or even up to 7 kind of thing. Well, maybe not 7, but like you could easily have to check more, and then it's definitely worth it. So only if you have a programmable calculator like this. You could use brackets. I'm going to use the fraction 2 bracket 4a. So you got to figure out how to get variables on yours. On mine, it's alpha, and then I use the red letters. I always use a. I don't know why. It's just closest. X is way over there. Plus 23. They're very picky about brackets when you're using the fraction. You've probably noticed that if you've done it. So you got to have brackets done properly in this case. Bracket x, which is now a, plus 2 bracket cubed. Nope. To the 4th. Equals. Okay, so that works. Sometimes it throws an error, and then that's a pain, and you got to go fix something. That time it worked. Okay. So now I'm going to go ahead and I'm going to punch my values. My first value has to be in the interval less than negative 23 over 4, which is negative 5.75. So I'll use negative 10. I take that value, I store it in A. Every calculator is a bit different, but that's how you do it. You type in the number, on mine at least. You type in the number, shift push this button for store, and then push that button for A. Then I just scroll up and hit equals. Negative. That's all I cared about that whole process, and I'm writing that down. Negative. What's in my next interval? It's between negative 5.75 and negative 2. So how about negative 4? Negative 4, shift, store A up equals positive. And then something bigger than negative 2. So how about 10, shift, store A up, negative, equals positive again. So we got two positives in a row. It happens. Okay, it's an asymptote, so that's no big deal. If it was something else, it would be more interesting and something you'd really have to think about. Now, this is concave down. This is concave up. This is a vertical asymptote. This is concave up. Everybody look. Change from concave down to concave up. That is a point of inflection. This is where we decide what it is. And the point, plugging it into my calculator, unfortunately, I can't use that program thing because that was the second derivative, and this has to go into the original function. Okay, but it works out to approximately negative 1.7. Any questions so far? We got one more thing we have to think about. What happened earlier that we ignored, but we need it for our graph? We found something earlier. Yeah, critical value of negative 4.5. And we haven't talked about it until now because normally it would be in our first derivative chart, but we didn't do one. What interval does that lie in? Negative 4.5. Is it less than negative 5.75? No. Is it between negative 5.75 and negative 2? Yes. So it's in an interval that's concave up. So what is it? It's concave up. The derivative exists at that point because it's where it was equal to 0. So I know it's a trough like this. So what is it? Local minimum. Thank you. It has to be, right? So negative 9 over 2, and I've already worked this one out, and it is about negative 1.8. So we locate critical points by determining which interval they're in, and is it concave up or is it concave down? And there's a little bit of an added complexity to it, whether or not the derivative exists. We'll talk about that more. That only comes up if you have special graphs that have cusps or vertical tangent lines, which we haven't done yet. We're not doing yet, but we might. Does that make sense? I think we got everything. Now we just have to sketch this bad boy. Man, where do you start? I almost want to take all of that information and list it all together. Not like everything, but like I'm going to go back and I'm going to look. Let's see. So I've got a y-intercept that's positive. I've got an x-intercept that is 2 x-intercepts plus or minus 3. I've got a vertical asymptote that's negative 2. So the vertical asymptote is to the right of my intercept. It's kind of what I'm thinking about. My horizontal asymptote is negative, so it's negative. My y-intercept's positive, so that's all good. That's going to be not so bad in terms of how to scale things. And then all my other points, these 2 points, are both to the left of my x-intercept. X-intercept was -3. These are -4.5 and -5.75. We good with all that? We'll see. So where do we start? I'm going to start with my intercepts and my asymptote. So my horizontal asymptote was -1. My vertical was -2. Oh, my vertical asymptote is slanted. I didn't notice that my ruler moved. Oh well. What next? I think I'm going to do my behavior around my asymptotes. If you remember, approaching -2 from the left and the right was both going up. Okay, from the left, positive infinity, right, positive infinity. So they're both going up. Horizontal asymptote going off to the left is below, off to the right is above. When you do it correctly, things come together in such a nice way that it just all makes sense. And you're like, yep, 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 yep. And if it's not feeling like that, probably something is off. But I know we're all different in how we visualize things and how good we are at that and how experienced we are, but that's the whole point of what we're doing is we're trying to gain that experience. So take a look, just put your pencil down and look up here. My point of inflection is at -5.75 around here somewhere, and my local mean is -4.5, it's around here somewhere, both to the left of -3. So when I come down, and I'm approaching from below, and I've got an x-intercept. So when I come down, I go through the x-intercept, I hit that local min. Whoops, that was kind of bad. Try that again. I come down, I go through the x-intercept, local min, and I have a point of inflection because as we said, you have, when you're approaching a horizontal asymptote from below, it's got to be concave down. This is concave up, clearly. So it's got to change to concave down. So it makes sense that there was a point of inflection there. If I had it wrong and my point of inflection was positive and it was over here, that would make no sense to all the other details of the graph. So I've got a local min here, and I believe I called that B. And I've got a point of inflection in here somewhere. It's hard to tell. But it all fit. It all made sense. Do you agree? And then this one, oh, I forgot my y-intercept, which is around here somewhere. It's positive. It was 9/4. Is that right? 9/4. So I'm coming down. What do you think? questions? Think we can squeeze another one in 9 minutes? I don't, so we're not going to try. The other one I have planned, actually, I realized is a lot like this one. It's just flipped. So probably not going to add us a lot of value, but it does bring back the point that I talked about yesterday, how like you got to be doing these because they don't all look the same. The one that you get on the quiz or the test will not necessarily look like this one. We've already noticed from MHF that these things can look very different, and there are all kinds of other ones. And they have points of inflection in different places, and they have different experiences as you go through. So like we can't do every type in class. We don't have enough time. So you've got to be doing this as well.